They stored energy without batteries in the 1800s, and the structures still exist today. Imagine a system that stores energy for days without using a single chemical battery. No lithium cells, no acid, no electronic components, just pure physics and mechanical structures that continue to function for generations. This isn't futuristic theory, it's 19th century technology that still exists operationally in various parts of the world. While today we rely on batteries that last a few years, before degrading, Victorian engineers built storage systems that have operated for over 150 years without replacing major components. The question isn't whether this technology worked. We know it worked because the physical structures are still there, many still in operation. The question is why such elegant and durable systems were largely abandoned in favor of technologies that require constant replacement. This roadmap will explore 10 different mechanical energy storage systems that were built and operated in the 19th century. We won't speculate on lost technologies or conspiracies. We'll examine documented physical structures that you can visit today, understand the simple physics that makes them work, and analyze why they represent solutions we've forgotten in the race for electrification. Each system demonstrates a different storage principle, from gravitational energy to pneumatic pressure, from angular momentum to thermal energy. They all share common characteristics. They do not degrade chemically. They do not require rare materials. They can be built with basic technology, and when well maintained, they operate for centuries. We begin with the most obvious and visible of these systems. If you're intrigued by the idea that 19th century engineers developed more durable energy storage systems than modern technologies, leave a like supporting the exploration of forgotten technical solutions that can inform current challenges. Subscribe for analyses of working historical technologies, not conspiracy theories. Turn on notifications so you don't miss investigations of systems that are still operating after more than a century. If you value an approach that examines physical evidence rather than making dramatic claims, click the Hypar button supporting content based on verifiable structures. The first storage system starts now. Gravitational water towers. Converted elevation into constant energy reserves. The first and most visible system. Water towers. Simple structure. A tank elevated 30, 50, sometimes 100 meters high. You fill the tank when you have energy available, usually during the day when windmills or water wheels operate at full capacity. The water remains in the tank for as long as necessary. When you need energy, you open a valve. Gravity forces the water down through pipes. The pressure of the falling water drives turbines that perform mechanical work. Elementary physics. Gravitational potential energy converted into kinetic energy. But implementation in the 19th century was surprisingly sophisticated. The tower in Colchester, England, built in 1883, is 43 meters high with a capacity of 900,000 liters. It was designed to provide constant water pressure for the entire city. The system operated continuously until 1987, 104 years of operation with the same brick and cast iron tank. There was no chemical degradation. Because there is no chemistry, only gravity. Maintenance consisted of repairing occasional leaks and replacing worn valves. The main tank was never replaced. Compare this to a modern lithium-ion battery that degrades 20% of its capacity after 500 cycles, typically 2 to 3 years of use. The Colchester Water Tower completed approximately 38,000 filling and emptying cycles in 104 years. The conversion efficiency wasn't perfect. Only 60 to 70% of the energy used to pump water returns as useful work when it goes down, but the durability more than makes up for it. And when the system fails, you know immediately. The water stops flowing. There's no catastrophic failure mode, no fire risk, no release of toxic chemicals. Gravity water towers were built in thousands of locations across Europe and North America during the 19th century. Many still exist as historical structures. Some still operate, supplying water. Pressure to fire suppression systems in older buildings. The technology is so obvious that we tend not to consider it energy storage. But functionally, that's exactly what it is. Converting intermittently available energy into energy available on demand through gravitational storage. Massive industrial flywheels maintain constant rotation by absorbing load variations. Second system, industrial flywheels. A solid cast iron wheel, 3 to 6 meters in diameter, 30 to 60 centimeters, thick, and weighing 5 to 20 tons, mounted on an axle with low friction bearings. Once set in rotation, the enormous mass resists changes in speed. This is energy storage through angular momentum. The physics, Rotational kinetic energy is proportional to the moment of inertia multiplied by the square of the angular velocity. Large mass distributed far from the center of rotation creates enormous moment of inertia. Variations in energy demand that would stop a small motor are absorbed by the flywheel without a perceptible change in speed. Practical implementation appeared in every 19th century textile factory. The main engine, usually a steam engine, connected to the flywheel via belts. The flywheel connected to the shaft line that distributed power throughout the factory. When weavers engaged and disengaged individual looms, this created abrupt load variations. Without a flywheel, the engine would have to constantly accelerate and decelerate, causing wear and inefficient operation. With a 10-ton flywheel spinning at 50 revolutions per minute, these variations were imperceptible. The flywheel stored energy when the load decreased and released it when the load increased, maintaining an essentially constant speed. The flywheel at the former Quarry Bank Mill textile factory in England, installed in 1820, is 5 meters in diameter and weighs 12 tons. It operated continuously until 1959, 139 years. It was removed not because it failed, but because the factory closed. The flywheel is now on display in the site's museum, still able to spin smoothly on its original bearings after 2 centuries. The storage capacity was not enormous in absolute terms. A typical flywheel stored perhaps 1 to 5 minutes of factory operation in kinetic energy, but for short-term stabilization, it was perfectly adequate. And unlike a battery that degrades with each cycle, the flywheel did not degrade. Wear was limited to bearings that could be replaced periodically. The flywheel itself, being a solid mass of iron, was permanent. Modern manufacturers of flywheels for energy storage in the electrical grid have rediscovered these principles. But contemporary flywheels use carbon composite materials spinning at extreme speeds in a vacuum, requiring sophisticated technology. 19th century flywheels were accessible technology. Any foundry could manufacture them, any mechanic could maintain them. Urban pneumatic system. Compress air overnight for daytime use. Third system. Compressed air distributed through an urban network. Concept. Compress air to 8 to 10 atmospheres during periods of low energy demand. Store in large tanks or underground tunnels. Distribute through piping throughout the city. Subscriber machines use compressed air to perform work. Paris built the most extensive system, operational from 1881 to 1914. Centralized compressors driven by steam engines compressed air at night when coal was cheaper and steam demand was low. The compressed air was stored in massive iron tanks in the basement of the plant. During the day, the air powered approximately 10,000 machines through 50 kilometers of piping. Pneumatic tools, elevators, synchronized public clocks, pumps, ventilation systems. The Parisian system was so reliable that it operated through 2 world wars. It was finally deactivated not because it failed technically, but because electrification offered greater flexibility. But aspects of the system survived much longer than anticipated. Some Parisian pneumatic clocks continued operating until the 1960s, powered by local compressors. The network of pipes still exists under the streets, now used for telecommunications. Conversion efficiency was modest. Only 30 to 40% of the compression energy returns as useful work at the point of use. But this was acceptable given the benefits. Superior safety compared to high-pressure steam. No risk of combustion. Compared to gas, possibility of large-scale storage. Distribution through inexpensive iron piping. London, Dresden, and Birmingham built similar systems, all operational for decades. The Birmingham system operated from the 1890s to the 1920s. New York had a pneumatic network from the 1890s to the 1930s, mainly for operating elevators in high-rise buildings. The durability of the components was remarkable. Air storage tanks built in the 1880s did not degrade because there is no chemical process. Iron may oxidize externally, but the interior of the tank remains protected. Piping required maintenance for leaks, but no inherent degradation. Compressors required regular maintenance, but were simple and repairable mechanical technology. The concept of storing energy as compressed air is now being revisited for grid storage. Modern compressed air energy storage systems use underground salt caverns to store compressed air powered by wind turbines, but the principle is identical to the Parisian system of 1881. Giant hydraulic accumulators maintain pressure for industrial and port machinery. Fourth system, hydraulic accumulators, a device that maintains constant hydraulic pressure regardless of variations in demand. Operation, a large vertical cylinder, usually 2 to 3 meters in diameter, 10 to 15 meters high. A massive piston slides inside the cylinder. The weight of the piston creates pressure in the hydraulic fluid below. When pumps add fluid, the piston rises, storing gravitational energy. When hydraulic machines demand fluid, the piston descends, maintaining constant pressure. The pressure was typically 700 psi, 50 atmospheres, sufficient to power powerful cranes, hydraulic presses, and dock gates. A more impressive implementation was in urban hydraulic power systems, similar to pneumatic systems but using water instead of air. London had the London Hydraulic Power Company operating from 1884 to 1977, 93 years of continuous operation. The system included 5 pumping stations, 300 kilometers of cast iron piping, and distributed hydraulic pressure to operate elevators, freight cranes, movable bridges, and industrial presses throughout London. Energy storage was provided by massive accumulators at each station. The accumulator at Tower Bridge, London, still exists and is occasionally demonstrated to tourists. Installed in 1894 to operate the bridge's lifting mechanism, it consists of 2 cylinders, each with a 120-ton piston. The combined mass of 240 tons of iron creates and maintains sufficient pressure to lift the bridge sections weighing 1,000 tons each. The system operated until 1976 when it was converted to electrohydraulic, but the original accumulators remain intact, demonstrating the durability of well-constructed hydraulic components. New York, Liverpool, Melbourne, and Buenos Aires had similar systems. All operated for decades with relatively simple maintenance. Efficiency was better than pneumatic systems. Approximately 60 to 70% of the pumping energy returns as useful hydraulic work. Leaks were a constant but manageable concern. The advantage over emerging electric systems was power-to-size ratio. A hydraulic winch could lift loads that required a much larger and more expensive electric motor. For high-power industrial applications, hydraulic systems remained competitive until the mid-20th century. Accumulators represent energy storage that is simultaneously simple, conceptually, and elegant in execution. No complex chemistry, just weight and gravity creating pressure. Durability was primarily a function of build quality. Well-manufactured cylinders operated for generations without degradation. Tidal mills captured energy from water level variations in reservoirs. Fifth system, tidal mills with storage via reservoir. The tide rises and falls twice a day, but you need continuous energy. Solution, build a dike that creates a coastal reservoir. During high tide, allow water to enter through sluice gates. Close the sluice gates at high tide. During low tide, water trapped in the reservoir is now at a higher elevation than the sea. Let the water flow back through a water wheel or turbine, generating power. This system stores energy not in moving objects but in the differential of water elevation. A tidal mill in Woodbridge, England, built in 1170, rebuilt in 1793, operated continuously until 1957. 787 years of operation in the same location. Of course, individual components were replaced multiple times, but the storage concept, the tidal reservoir, remained identical. The reservoir is approximately 3 hectares with an average depth of 2 meters and stores about 60,000 cubic meters of water. With a tidal differential of 3 meters, this represents approximately 500 megajoules of potential energy per tidal cycle. The original water wheel was replaced in 1957 by a modern turbine. The mill was restored and in 2010 began generating electricity connected to the national grid. The same reservoir structure built in 1793 remains operational after 230 years. Maintenance consisted mainly of repairing the dike and replacing the water wheel or turbine when the reservoir itself requires no maintenance beyond sedimentation. France had over 100 operational tidal mills in 17. The Bréhat tidal mill in Brittany, built in the 12th century, operated until the 1920s. The reservoir and dike still exist intact. Efficiency was respectable. Approximately 60% of the available potential energy was converted into useful mechanical work. Storage capacity was significant. A tidal reservoir could supply power for 4 to 6 hours after each high tide, essentially creating half-day energy availability from a source that naturally occurs for only an hour or two. This is exactly the challenge that modern batteries face with solar. Power. An intermittent source needs to be converted into a continuous supply. Tidal mills solved this for tidal energy more than 800 years ago using only stone structures, wooden sluice gates, and gravity. The concept is being revisited now in modern tidal energy projects, but with sophisticated turbines and contemporary materials. The storage principle is identical to that used by medieval builders. Mechanical clock towers use descending weights for continuous weekly operations. Sixth system, clock towers with drive weights. This may seem trivial compared to industrial systems, but it represents extremely efficient and durable energy storage. How it works. You lift heavy weights to the top of the tower using a crank. The energy from your muscular work is stored as gravitational potential energy. During the following week, weights descend slowly, releasing energy in an extremely controlled manner through a mechanical escapement. This energy powers the clock and bell mechanism. Big Ben in London, installed in 1859, uses this system. The main weights that drive the timekeeping mechanism weigh 312 kilograms. The weights that drive the bells weigh up to 1,200 kilograms. These weights descend approximately 2 meters per day. The clock keeper climbs the tower 3 times a week to manually lift the weights. The system has operated continuously for 165 years with the same basic mechanism. Maintenance has consisted of repairing worn escapement components and lubrication, but the weights and storage tower remain unchanged. Hundreds of similar clock towers exist throughout Europe, many operational for over 200 years. Salisbury Cathedral, England has a clock installed in 1386, the oldest continuously operating clock mechanism in the world. 638 years using the same principle of gravitational energy storage. The efficiency is remarkably high, approximately 80 to 90% of the energy used to lift the weights returns as useful work through the mechanism. Durability is a function of simplicity. Weights are inert mass of iron or stone that does not degrade. The tower is a masonry structure that can last for millennia. The energy release mechanism, the escapement, is a more complex component, but is still purely mechanical and repairable. Compare this to a modern electronic clock that requires a new battery every year or two. The gravitationally stored energy tower clock operates for decades between significant maintenance. The scale of storage is small, perhaps only a few megajoules of total energy stored in the weights. But for the specific application of precise timekeeping over periods of days, it is a perfectly adequate solution, and it demonstrates an important principle. Energy storage through gravitational lifting of mass is inherently durable because there is no chemical or physical degradation process. Elevated mass remains elevated until you allow it to come down. Counterweight systems in mines lifted loads by lowering another load. Seventh system, counterweights in vertical transport systems in mines. The challenge, you need to lift heavy ore from the bottom of a deep mine. This requires significant energy, but at the same time, you need to lower equipment, timber, and workers into the mine. Elegant solution. Connect 2 wagons by cable over a pulley at the top of the mine shaft. When one wagon full of ore goes up, another wagon full of material going down provides the force. You only need to add energy to overcome friction and occasional imbalance. Most of the energy comes from the descending load itself. The system stores energy in the sense that elevated mass represents potential energy that can be recovered during descent. But more importantly, the system balances ascending and descending loads, minimizing external energy required. The copper mine in Røros, Norway, operational from 1644 to 1977, used a counterweight system for vertical transport. The 1887 mechanism still exists in the site museum. During 333 years of operation, the principle of the counterweight remained central to mine transport. Cornwall, England, had dozens of tin and copper mines using counterweight systems during the 19th century. The Givor mine, operational until 1990, had a system installed in 1911 that was still functioning at the time of closure. 79 years of operation, with regular maintenance, but without fundamental redesign. Efficiency was excellent. When loads were well balanced, perhaps 90% of the potential energy of the descending load was transferred to lift the ascending load. Additional energy required was only to overcome friction in pulleys and bearing. Component durability was good. Steel cables required periodic replacement due to fatigue. Pulleys wore out and were replaced, but the basic structure and operating principle remained unchanged for generations. Compare this with modern motorized lifting systems that require large electric motors consuming energy continuously. Counterweight systems are inherently more efficient because they recover gravitational energy from the descending load. This principle is now being applied in modern high-rise building elevators, where the elevator always has a counterweight to reduce energy requirements. But the concept was developed and perfected in 19th century mines, where energy efficiency was a critical economic necessity. Water wheels and dams created storage ponds for nighttime operation. Eighth system, mill ponds with controllable dams. River flow varies seasonally and daily, but you need to operate the mill consistently. Solution: build a dam creating a pond that stores water during periods of high flow. During periods of low flow or when you need extra power, release additional water from the pond through the water wheel. The pond acts as a hydraulic power. Battery. Slater Mill in Rhode Island, United States, built in 1793, had a storage pond system that allowed for nighttime operation. The textile mill operated 24 hours a day when needed, using water stored during the day to supplement river flow at night, when demand from other mills on the same watercourse decreased. The system operated until 1919, 126 years of operation with the same basic pond and dam. Lowell, Massachusetts, developed a complete system of canals and storage ponds between 1820 and 1850 to supply textile mills. The system included dams, distribution canals, control gates, and multiple storage ponds. It allowed the operation of over 40 factories with complex sharing of water resources. Many structures of the Lowell system still exist, and some still control water flow through the area. Storage capacity depended on the size of the pond. A typical mill pond could store the equivalent of 4 to 12 hours of operation in potential energy. This was sufficient to stabilize daily flow variations and allow for more flexible operation. Efficiency depended on minimizing losses due to evaporation and seepage. Well-constructed ponds with clay bottoms lost little water. Maintenance consisted of repairing the dam and cleaning sedimentation that gradually reduced storage capacity. But the stone structures of the dam could last for centuries. England has mill dams built in the medieval period, still retaining water after more than 500 years. The difference between a mill pond and a modern hydroelectric reservoir is mainly one of scale. The principle is identical. Store energy as water elevation. Release it when demand exceeds instantaneous supply. Modern pumped storage systems use this concept on a massive scale, pumping water into an elevated reservoir during periods of low electricity demand and releasing it through turbines during peak demand. Spring systems in precision mechanisms provided compact and portable power. Ninth system: steel spiral springs in timing and control mechanisms. Unlike the large-scale gravitational systems discussed earlier, springs represent energy storage through elastic deformation. You twist or compress the spring, storing energy as tension in the metal. The spring returns to its original shape, releasing energy in a controlled manner. 19th century marine chronometers relied on this storage. John Harrison developed highly accurate marine chronometers in the 1700s that revolutionized navigation. These devices use large spiral springs as energy storage. Once wound, they provided constant power for 24 to 48 hours. Accuracy was critical for navigation. An error of a few seconds per day resulted in positional errors of many kilometers at sea. Harrison's chronometers still exist, kept at the Royal Observatory, Greenwich. The H4, completed in 1761, was tested on a sea voyage to Jamaica in 1761-1762 and lost only 5 seconds in 81 days. After 263 years, the mechanism can still operate when carefully maintained. The durability of high-quality steel springs is remarkable. When designed to operate within the material's elastic limits, springs can complete millions of cycles without significant fatigue. Marine chronometers were wound daily, completing approximately 25,000 cycles in a typical 70-year lifespan. Well-manufactured springs lasted this entire lifetime without replacement. Storage efficiency is excellent. Approximately 90 to 95% of the energy used to wind the spring returns as mechanical work. Losses are mainly due to friction in the release mechanism and air resistance to moving components. Energy density is modest compared to modern batteries, typically only a few hundred joules per kilogram of spring, but for low-power applications operating for days, it is adequate. Modern mechanical wristwatches still use coil springs, demonstrating that the principle remains viable for certain applications. But the concept of the spring as energy storage was explored on a much larger scale in the 19th century. Industrial control mechanisms, speed regulators, safety systems all use springs to store energy and release it when needed. The simplicity and reliability of springs made them fundamental components in the pre-electrical era. Mass thermal storage of iron maintained heat for nighttime heating. 10th and final. System: solid mass thermal energy storage. Less recognized as energy storage, but functionally equivalent. Concept: heat a large mass of material with high thermal capacity during the day when fuel is being burned for other purposes. The mass releases heat slowly during the night, maintaining temperature without further combustion. Most common implementation: mass stoves, and masonry heaters. Large brick or stone structure with complex internal channels. You burn firewood intensively for 2 to 4 hours, heating the entire mass to 400 to 600 degrees Celsius. After the fire goes out, the mass radiates heat for 20 to 24 hours, keeping the environment warm. The mass functions as a thermal battery. Nordic countries and Central Europe developed mass heater technology to a high degree of sophistication during the 18th and 19th century. The Austrian Kachelofen and the German Grundofen were multi-ton structures of ceramic and masonry occupying an entire room wall. Once heated, they kept the house comfortable for an entire day with only one burning period. A Kachelofen built in 1820 in an Austrian rural home still operates today. 204 years of service with the same masonry structure. Maintenance consists of cleaning soot channels annually and occasionally replacing damaged internal refractory bricks. But the main storage mass never needs replacing. The efficiency is surprisingly good, approximately 70 to 80% of the energy content of the burning firewood is eventually transferred to the environment as useful heat. This is significantly better than a conventional metal stove where much heat escapes through the chimney. The storage capacity is significant. A typical 3 to 5 ton mass heater stores approximately 100 to 200 megajoules of thermal energy when fully heated. This is equivalent to the energy in approximately 5 to 10 kilograms of firewood. Industrial applications of thermal storage were even larger. Brick kilns for ceramics accumulated heat in masses of 100 to 500 tons of refractory masonry. Once heated, they maintained temperature for days, allowing processing of successive batches of products with minimal additional heating. The Wedgwood pottery in England used enormous bottle kilns that operated on this principle from the 1700s to the 1900s. The refractory brick structures lasted for decades between reconstruction. Thermal storage is now being revisited for concentrated solar power system, where heated molten salt stores daytime energy for electricity generation at night. But the principle of using solid mass as a thermal battery was developed and perfected centuries earlier by heater and furnace builders. If these 10 19th century mechanical and thermal energy storage systems demonstrated that engineers of that era developed elegant and durable solutions to challenges we still face today, supporting the exploration of functional historical technologies that can inform current choices. Subscribe for more analyses of forgotten technical systems that operated for generations. Click on the video appearing on the screen to continue exploring technologies that worked without reliance on complex electronics or chemistry. Thank you very much for taking the time to understand that durable solutions have often already been developed and may only need to be adapted to modern contexts. See you in the next exploration of verifiable historical technology.